Hey, my name is Elishai Ezra Tsur, and I am heading the Neuro and Biomorphic Engineering Lab at the Open University of Israel. This project was led by Hazan, a PhD student for computer engineering in the lab, with the support of Professor Shlomo Greenberg from Ben-Gurion University. Geophones are acoustic detectors that respond to seismic waves, which generate ground vibrations. In this work, we utilized a neuromorphic Legendre memory units, or LMUs, for low-power, real-time classification of geophone data, discriminating vibrations which were generated by human footsteps, a moving vehicle, and ambient noise. Designed specifically for time series processing, the LMU maintains a compressed representation of recent inputs to a continuous time state-space model. It leverages a continuous time state-space model to encode the temporal history of inputs more efficiently than conventional LSTM models.
A geophone is a ground-mounted sensor that converts mechanical ground motion to electrical signals. It typically consists of a magnet suspended in a wire coil, where the relative motion between the coil and the magnet induces a weak and often noisy current proportional to the vibration of the ground. We designed two experimental settings measuring human footsteps and a moving vehicle. For human data acquisition, 42 geophones were planted underground in an agricultural field. A subject walked near the field, generating vibration that varied in strength based on their distance from each sensor. The vehicle dataset was recorded using 12 geophones, planted in a greater spacing. We studied two recurrent memory architectures, LMU and LSTM. The raw input signal is first processed through a STFT block to extract time frequency features. These features are often fed to an LMU layer to capture temporal dependencies efficiently. The LMU output is passed through a series of dense layers to generate the final multi-class predictions. Our results demonstrate that both the LMU and the LSTM architecture are highly effective at classifying geophone signals. While the LSTM model demonstrates superior accuracy, the LMU model offers significant advantages for edge development as it allows for energy-efficient neuromorphic hardware design as mentioned earlier. Moreover, in contrast to LSTM networks which rely on gated recurrent structures with relatively high memory and computational demands, LMUs implements a principal state-space memory mechanism which makes them better suited for real-time inference.
We would like to thank our funders and partners, and we are looking forward to seeing you all in the conference.